Welcome, everyone, to our presentation on binary integrated circuit counters. Today, we'll explore the exciting world of digital circuitry. Meet our group, David Duran, Elijah Reyes, and Enzo Tambagan, Siddharth Jain, Kyle Malutaw, Albert Jacob, and lastly me, Eric Jen Ramilo. Today, we'll unveil the magic behind binary counting mechanisms and revolutionize complex binary calculations. Let's dive right in. Binary circuit counters are integral to digital electronics to track and process data using sequential logic circuits. They're widely employed for counting in various electronic applications. These counters efficiently manage digital data by transitioning through binary states, incrementing or decrementing with input pulses. Found in frequency measurement, event monitoring, and data processing, they offer reliable counting capabilities, leveraging binary logic and sequentially circuitry. They provide robust solutions for managing digital data, making them indispensable in modern electronics.
The binary system is a numerical system based on two symbols, typically represented as 0 and 1. In this system, each digit's value is a power of 2, with the rightmost digit representing 2 to the power of 0, the next digit representing 2 to the power of 1, and so on. This system is fundamental to digital electronics and computing because it aligns well with the on and off states of electronic switches, making it ideal for representing and manipulating digital data. A circuit diagram is a graphical representation of an electrical circuit using symbols to denote components and lines to connect them. In digital electronics, circuit diagrams are used to illustrate the connections and functions of various components such as logic gates, flip-flops, and other elements crucial for processing digital signals.
Digital counter design refers to the process of creating circuits that can count digital signals. A digital counter typically consists of flip-flops and logic gates configured in a sequential manner to count input pulses. So depending on the application requirements, counters can be designed to count up, count down, or count in other predefined sequences. The design process involves selecting appropriate components, arranging them accordingly or according to the desired counting sequence, and ensuring proper timing and functionality to achieve accurate counting.
Sequential logic in a binary circuit counter allows for sequential storage and processing of binary data. To implement binary arithmetic in a counter, flip-flops are used to represent binary digits. Each flip-flop's output is connected to the next flip-flop's clock input, creating a ripple effect for counting up or down. These gates also control when each flip-flop changes its states based on the current count and clock signal.
Efficient binary circuit counters play a crucial role in digital circuit design by efficiently managing the counting process. They leverage sequential logic and binary arithmetic principles to store and process binary data effectively. So, by carefully designing the sequential logic using flip-flops and logic gates, the counter can count up or down with minimal circuit complexity. One key consideration is clock management, ensuring proper synchronization and timing between flip-flops to maintain reliable operation. Additionally, engineers must choose between parallel and serial counting methods based on the application's requirements. Parallel counters offer faster operation by counting multiple bits simultaneously but require more circuitry, while serial counters count one bit at a time, therefore reducing complexity at the cost of speed.
Hello ma'am, my name is Kyle, and now for this slide, another important aspect is handling counter resets and overflow conditions. When the counter reaches its maximum value, it can either reset to 0 or wrap around to continue counting, depending on the application's needs. By optimizing these aspects of binary circuit counter design, engineers can create digital circuits that efficiently fulfill their intended functionality while maximizing performance and minimizing resource usage. That's all. Thank you.
So we move on to what is a binary circuit counter. So a binary circuit counter serves as a efficient counting mechanism that simplifies complex binary calculation effortlessly. By employing sequential, logic, and binary arithmetic principles, it systematically processes binary data with ease. This counter's efficiency lies in its ability to seamlessly increment and decrement binary the numbers, streamlining the counting process without irritating manual intervention. Its sequential design, typically constructed using a flip-flops and logic gates, ensures smooth progression through binary values. Moreover, this counter minimizes the complexity associated with binary arithmetic, enabling straightforward implementation within digital circuits. With each clock cycle, it accurately manages the count, simplifying tasks that involve extensive binary calculations. So that's a brief summary of what is a binary circuit counter.
A binary counter, integral to digital electronics, relies on flip-flops as basic units to count in binary. Each flip-flop corresponds to a specific bit in the binary count, forming the counter structure. Clock pulses drive the counting process by triggering incrementation through flip-flops, ensuring systematic progression on the count. This mechanism enables precise tracking of binary representation, facilitating essential functions like timekeeping, data processing, and many things in the digital systems. In essence, a binary counter is a cornerstone of a digital circuitry utilizing flip-flops to incrementally count in binary and controlled by clock pulses. It maintains accuracy and reliability, serving diverse digital applications such as timekeeping, frequency measurement, and data processing.
Okay, for this slide, the binary bit clock is a timing signal used in digital system that indicates when each individual bit of a binary number should be processed or sampled. It synchronizes the operations of various components within a digital system, ensuring that data is handled consistently and accurately. A binary sequence generator is a circuit or algorithm that produces a sequence of binary numbers according to a specific pattern or rule. These generators are often used in digital signal processing, communication systems, and cryptography, among other applications. They can create sequences such as a counting up or down, alternating patterns, or more complex sequences based on mathematical formulas. And that's all. Thank you.
While binary comparator is a digital circuit or a software component that compares two binary numbers and determines their relationship, typically whether they're equal, greater than, or less than on each other. It examines corresponding bits of two numbers and generates outputs, signaling indicating the result of the comparison. As you see, binary can be used in many applications. There are countless things that we can do. We can have many arithmetic logic units that we can use, and you can use it in basically data processing and certain processor, decision making, sorting, data validating, everything. We're all controlled by binary. So yes.
So moving on to the schematic diagram, first let us discuss what is the Arduino Uno. So the purpose of the Arduino Uno in the schematic diagram is to be the main source of power into the circuit breadboard. And then we can see that the 5 volts is connected to the positive charge of the breadboard through an R2 or resistor, and is also connected to the VCC pin of the binary counter IC. And then lastly, we can see that the ground port of the Arduino Uno is connected to the negative charge of the breadboard. And then, first let us discuss the R3 to R5. So these are just resistors made for handling any sort of electricity flow to the circuit, as these are connected to the IC and also the diodes. So diodes are represented as D1, D2, and D3, which are just the LEDs responsible for displaying the output of the counter IC. So moving on to the counter IC, we know that VCC is connected to the power source, and then CP0 and ZP1 is what handles the inputs that any sort of it will receive from the breadboard or the circuit. So in our case, we use the push button in our project. So whenever a push button is pressed, it will be received by CP0 and ZP1. And then it will iterate the count by 1, 2, and 3, depending on which is connected to the Q pins. So we now move on to the Q pins, which are Q0 up to Q3. We can see that Q0 is not connected to any ICs or any wires into the breadboard, because the Q0 represents only a 2-bit binary or a 1-digit. It can change only from 0 or 1, which is useful in other projects. But in our case, we chose Q1, Q2, and Q3 to represent a 4-bit binary which has 3 digits that can change from 0 to 1. So for example, it can be 111, 110, 001, or 000. So any of the latter. And then now we move on to the ground pin. So this ground pin is just connected to the ground pin of the breadboard. And then we move on to the MR2. So what does the MR2 does? So MR2 is just a pin that receives any form of inputs. It can be from the positive or the negative charge on the breadboard, which doesn't really matter, as this can be interchangeable from our MR1 or MR2, and it will make the binary counter IC just fine. And then we may see that the R5 and D3 is disconnected, but it is because that it doesn't fit the schematic diagram made for the project. So it kind of went over beyond the limit on what the Tinkercad can display horizontally to the schematic diagram. So that's why it's looks like it's disconnected, but is connected to this label. So we can see that U binary counter IC Q3 is the same as the ones on the above and the below. And that's it for the schematic diagram. So now we move on to the hardware simulation of the project. So we can see that the Arduino Uno is on the left, which has 2 wires that is connected to the breadboard. So we know that the purpose of it is to just apply a power source to the breadboard circuit that we have made. And then we can see that the binary counter IC here is the 74HC93 or either a 74LS93 IC chip, which is just the same. And then we can see that there are 3 LEDs. So every time a button is pushed, one of the LEDs will light up based on the binary bit counter. So for example, let's press a 1. So whenever a button of 1 is pressed, it will iterate through the counter of the ICs. So the first LED will light up, then it will unlit upon the second button, and it will lit the second LED. And then upon another button press, it will light up the first LED again, and then the second LED will remain still because it doesn't receive any form of inputs. And then whenever a button is pressed again, we can see that the 2 LEDs will unlit, making the third LED lit based on the bit binary. And so that's it for the hardware simulation in the digital or virtual scale. And now we move on to the actual physical hardware simulation itself. And then whenever we see that a button is pressed, one of the LEDs will light up. And whenever another button is pressed, we can see that the second LED will light up, making the first one unlit. This is due to the binary counter IC giving the outputs for the LEDs. And then once all of the LEDs have lit up, and then a button is pressed, the simulation will reset back to 0, or when the count itself reached its maximum in the bit binary counter IC. So it will reset back to the count of 0. And then the simulation or the sequential logic itself will repeat every button press. So we can use this in real life examples based on the state of the IC. So we can determine whether the IC is at its lowest when no LEDs are powered up, and we can determine when the IC or the circuit is at its maximum state or at its final state based on all of the LEDs lightening up. And that's it for our hardware simulation through physical hardware itself.
Thank you for watching, ma'am. I just want to say, Sana 100, thank you po, and God bless, thank you.